from our transformations unit. In this example, I've given you the graph that you can see on the screen right now, and what I'm asking you to graph are a bunch of transformations that are associated with this graph, as you can see on the right side of the screen. Before we start though, I figure we might as well talk about how did I even get to this function. This function that you see right here is a transformation of the absolute value function, which Desmos understands as abs of x. So how did I even get to the function that we've got graphed over here? Well, a couple things that you might notice are this. One, it looks like my black graph, the absolute value of x, has a vertex at 0, 0, whereas the purple graph, the graph that you aren't sure of what the equation is at 2, 0. It seems like one of the things that I did here to make the purple function out of the black function here is I shifted the black function to the right by 2. How do we perform a shift right by 2? Well, since it's a horizontal adjustment, I know that adjustment will occur inside of our function to x. Since it is a shift, I know that it will be additive or subtractive. And I know that all of my internal adjustments, my horizontal adjustments, they always happen the opposite of my intuition. So when I would traditionally think to move to the right would be +2, in this case, the opposite of my intuition says -2 is going to go ahead and shift us to that appropriate location. The next thing that I can see is that all of the points on the black graph here at a given x value all seem to be about half as tall as their corresponding y value on the purple graph. If you go to the point 5 here, we can see a height of 3. And I go to the point 5 on the other graph and we can see a height of 6. It seems to be twice as tall. So how do I make my black graph be twice as tall as it used to be? I can multiply the outputs from the absolute value function by 2, and you can see that this is how I've constructed the function that we've built here. I began with the original absolute value function, I shifted it to the right by 2, and I made it twice as tall at each of the points that we were viewing it as. So I'll go back to just viewing the original purple graph as we had originally seen it. The other cool thing that we can do here is we can actually use Desmos to help us out with these functions here. Desmos is cool with this function notation, so we're going to be able to do these transformations here, but the important thing is that you're able to predict these, because what's going to happen on our upcoming test is I'm going to ask you a question exactly like this, except you're going to have no idea what the actual equation was that represents the function, so you won't really be able to get away with using Desmos to come up with your answers. But you should be able to play some of these guessing games here and see that Desmos does agree with your intuition. So we're going to be able to literally just type in each of these things into Desmos. Since f of x is defined, it's going to be able to understand how to graph each of those. So our first one here is f of negative x. The important thing we want to do is predict before we look at our answer here. When I see that negative, I see first of all that it is inside the parentheses, so I expect that this is going to affect our inputs. I expect that this is going to be somehow some sort of horizontal transformation that we're making. When I think of f of negative x, what this says to me is all of our inputs that used to be positive are now negative, and all of our inputs that were negative, we've applied a negative to them, so they should become positive. So I'm expecting to see all the parts of our graph that are to the left of the y-axis here. These all have a negative x value. These should all keep their same y values, but have the opposite signed x value. So I think this piece here is going to flip over to the other side. Similarly, all of these values over here, all these locations with positive x values, their y values are going to stay the same, but their x values are now going to become the negative of what they once were. So these are all going to flip over to the other side. This f of negative x we should recognize as a left-right flip over the y-axis right here. I know it's a horizontal flip because the adjustment is being made inside the parentheses. So I can just go ahead and ask Desmos to graph f of negative x for me, and you can see that we do indeed perform a vertical flip, or excuse me, a horizontal flip over the vertical line y equals 0, right? Or excuse me, x equals 0 is the vertical line over which we are reflecting here. So this is a horizontal reflection, or a left-right flip, as I somewhat more loosely generally refer to it. Our next example that we can see here has the negative instead on the outside. So my intuition tells me that this negative is still going to perform some sort of flipping action, but it still looks like this time the negative is on the outside of the function here. So I'm expecting this to affect my outputs. My y values are what I expect to get flipped. I notice in this case that the entire function that I'm seeing right now has all positive y values. I'm expecting when I negate all of the y values that the x values will stay the same, but they'll all have the negative for their corresponding y value. And when I graph negative f of x here, I do see exactly that. This is a vertical flip. We have reflected over the horizontal line y equals 0 here. We have taken what all of our old y values were, and we have negated each of the y values to come up with the new y value on our transformed graph. Before I walk away from this one real quick, I do want to show here that if we had instead shifted this function up by 1 to begin with, then when we perform this vertical reflection, it's not like we're reflecting at the vertex. Our line of reflection is the x-axis right here. So when we mirror over the x-axis on this graph here, just like there was a gap between of height 1 here, there is a similar gap of height 1 on the other side. This is a true mirror image over the line y equals 0 in this case. Let's go back to our original here. Get rid of this guy. Our next one was me being dumb right there. I just had a repeater, so I guess we'll go ahead and skip that one. The next graph that I see here is negative 0.5 f of x. So I'm going to think of this as two different transformations. The first transformation is the negative on the outside. That's going to go ahead and tell me, as we just saw, to perform our vertical flipping. The next transformation is this 0.5 in front of the f of x. This says whatever your outputs were, whatever your heights were on f of x, only keep half of that height. So I'm expecting, for example, this y-intercept value that's at 4. First, I expect it to be vertically flipped to become negative 4. Then I expect us to only keep half of the associated heights. So I'm expecting to see a less steep straight line here. Then I expect to see a y-intercept is sort of like my guide point here to be at this point of negative 2. So let's go ahead and take a look here. Negative 1/2 f of x. And what I do see is that our graph before had lines of slope 2 and negative 2. Our lines now have slopes of 1 and negative 1. They're only half as steep. We're only keeping half the height. As predicted, we did get our y-intercept to be at negative 2. It started at positive 4. We reflected it to negative 4. We kept half the height to get it to be at negative 2 right there. So this was a vertical flip, and then only half the height. We squashed it by a factor of 1/2. Our last one here, f of negative x plus 3. Again, we have two transformations going on. The negative on the inside is going to tell me to negate all of my x values. That should be a left-right flip. So I'm picturing things like our 4 should stay the same, because as we reflect that over the y-axis, it doesn't go anywhere. This vertex point at 2, 0, I expect to reflect over the axis to be at negative 2, 0. But then we're going to go ahead and add 3 to all of our outputs from the f of negative x function. These are our output values, and we're going to add 3 to all of our outputs. That means our y values are all going to be 3 times larger. So after I reflect here, I expect my vertex to land at negative 2, 0. Then I expect to shift the entire graph up by 3. So I'm anticipating seeing things like a vertex here at negative 2, positive 3. So let's go ahead and take a look here. F of negative x does the reflection left to right like we expected. And when I add 3, it is going to add 3 to the height of all of the points that were on my graph. I do see that vertex location at negative 2, 3. I do see that my y-intercept did not get changed by the reflection. It stayed at a height of 4, but then it did get shifted up by 3 to reach a height overall of 7. So again, if you guys want to see any more of these examples, especially in this very graphical unit, I can do these screen share things here. So let me know if there's anything else you want to see.